Hello everyone, now we're going to show the proof we talked about in the last episode. So this is the proof for the proposition on the conditional probability function. We say that it is a probability, so we are going to show that this is a probability. We need to verify that the function going from R tribe into R, associating A with the probability of A knowing B. We need to show that this function verifies the properties of a probability. As in the measure theory, the properties of probability in measure defined in measure theory. The first axiom, the first property is P of, it is, let's call this function f, it is f of omega equals 1. But f of omega is also the probability of omega knowing b, which is the probability of b intersected with omega divided by the probability of b, but b is included in omega in our universe, so this is the probability of b intersected omega equals b, because b is here, omega is here, so of course the intersection is b. So we have then P of b over P of b. This is equal to 1. The first property is true. Then let's take a sequence of events with I belonging to n, and our sequence is in omega n. Our set of events are disjoint. If we take two events in the sequence, they will be disjoint mutually. So let's look now at the events B intersected with AI, following events. We have AI intersected with AG. If E is different, then it's not equal to J. So our events B intersected with AI are mutually disjoint. If we take intersection with B intersected AG, we'll have, this is a void. Now we can look at the probability of the union of AI knowing B. We want to look at f of the union of our mutually disjoint set, and we want this to be equal to the sum of FAI. So now let's look at FUAI knowing B. It is the probability of the union of AI intersected with B divided by P of B. But this is also the probability of the union of the intersection of B with AI divided by probability of B. Because if you take a union of events and you look at the intersection with an event B, you have A1, A2, A3. It's the same thing as looking at the union of this quantity. And they are the B intersected A1, B intersected A2, B intersected A3. This is, as we know, P is a probability, so we have the property. We have the star property that is true for P, since we know it is a probability by hypothesis. So it's equal to the probability, the sum of the probability from y equals 1 to n, for y belonging to n, of the probability B intersected with AI over P B. This is the sum for y in n of P B AI intersected with AI divided by P of B, and this is also the sum of the probability of AI knowing B. So we just saw that f of the union of AI is equal to the sum of the FAI. We can then say that our function P, we can denote this like that, the function f it verifies the sigma additivity property, and that's the end of the proof. We have shown that P knowing B is a probability. Now let's talk about an example to apply this, to apply what we saw. We consider the probability P of u, Pu, defined on a space omega, a finite space with the tribe P of omega. Pu of an event is as follows. It is the cardinal, the number of events in the set A divided by the number of events in the universe omega, in the space omega. If the event B is impossible, that means if it is not impossible, that means it is different than the void set, its probability is strictly positive. And for all event A, we have P of the probability Pu of A knowing B is equal to Pu A intersected with B over P B, which is the cardinal of A intersected B divided by the cardinal of B. If A is included in B, this formula can be reduced to Pu of A knowing B equals cardinal of A over cardinal of P of B, as we saw it earlier. This shows that for events A such that A is in B, the conditional probability P the conditional probability P of u PU knowing B is equal to the uniform probability of on B. But there are no, be aware, there is not a simple relation between a conditional probability of an event and its simple probability. There is not a simple order relation, between the conditional probability of an event and its probability, like we are going to see in a little exercise. We throw 2 dice. 2 dices. We throw them and we consider the events A. The sum is 5. B. The first dice gives 3. C. The first dice gives at least 3. We want to know P of A knowing B, and P of A knowing C. The solution: we have P of A, probability of the sum to be equal to 5 is 4 over 36. This is 1 over 9. Probability of B equal to 1 over 6. Because there's only 3 over the 6, all the 6 dice, or the 6 numbers the dice can give, so kind of fair, it is 1 over 6. And for P of A, you just have to count the possibilities, the possible occurrences to obtain 5 from the summation. You have 3 and 2, you have 2 and 3, and you have also 4 and 1 and 1 and 4, and that's all. So it is 4 over 36, and when you simplify by 4, you obtain 1 over 9. So now we want to look at P of A and B also, and this is P of A intersected with B, so the sum when the first dice gives 3, and there is only one case where it happens. It's P of A intersected with B. This is very simple. It is the sum is equal to 5, knowing the first dice gives 3. So you have 3, then 2. It is equal to 1 over 6. Yeah, so it is P of A intersected with B over P of B. P of A in B. It is equal to 1 over 36 divided by 1 over 6, and it gives 1 over 6. Sorry. The conditional probability of A knowing B is bigger than the probability of A. We have P of A knowing B greater than P of A. But we also have P of C equals 4 over 6 equals to third, and P of A intersected with C equals 2 over 36 equals 1 over 18. we then have of P of C 2/3 P of A intersected with C equals 1 over 18. So we found that P of A knowing C is 1 over 12, the conditional probability. Of A knowing C is smaller than the probability of A. So P of A knowing C is smaller than P of A. So we observed that we can have P of A knowing B greater than P of A, and P of A knowing C smaller than P of A. There is not another relation. And so that is the end of this video. In the next video, we're going to talk about the Bayes formula. I hope you learned a lot of things. See you.